Every night you look up and the moon is there. It has always been there. Your parents saw it. Every civilization that has ever existed on this planet saw it. It feels permanent, fixed, eternal. It isn't. The moon is leaving, not metaphorically, not eventually in some abstract astronomical sense. Right now, tonight, as you read this, the moon is 3.8 centimeters further from Earth than it was exactly 1 year ago. That's roughly the rate at which your fingernails grow, slow enough to ignore, fast enough over geological time to end the world as we know it, and the consequences of its departure are far stranger and far more total than almost anyone realizes. To understand what we're losing, we first need to understand what the moon actually does. Most people think of it as a light source, a romantic backdrop, something that controls tides. That's like describing a surgeon as someone who washes their hands. The moon is a stabilizer, a gravitational anchor. Earth's axial tilt, the angle at which our planet leans as it orbits the sun, sits at approximately 23.5 degrees. That tilt is what gives us seasons. It is what makes large parts of Earth habitable. Without it, the climate patterns that allowed complex life to emerge simply would not exist, and the moon is what holds that tilt in place. Without it, Earth's axial tilt would not stay at 23.5 degrees. Computer models suggest it would swing chaotically, anywhere between near zero and over 85 degrees, on timescales of millions of years. At 85 degrees, Earth would essentially be rotating on its side. Polar regions would face the sun directly for months. Equatorial regions would freeze. The climate would not shift gradually. It would lurch, violently, repeatedly, with no stable equilibrium for life to adapt to. Mars has no large moon. Mars's axial tilt has varied between 10 and 60 degrees over its history. Some researchers believe this is one of the reasons Mars, whatever it once was, is now what it is. We are not Mars. Yet. But we are heading somewhere. The mechanism behind the moon's retreat is tidal friction, and it begins with the ocean. The moon's gravity pulls on Earth's oceans, creating the tidal bulge we call high tide. But Earth rotates faster than the moon orbits. This means the tidal bulge is always slightly ahead of the moon, pulled forward by Earth's rotation. That bulge has mass, and that mass exerts a gravitational pull back on the moon, nudging it forward in its orbit. In orbital mechanics, more speed means a higher orbit. The moon accelerates slightly, it moves outward, energy is conserved. So where does the energy come from? From Earth's rotation. Every time this happens, every single tide cycle, Earth's spin slows down by an almost imperceptible amount. The days are getting longer. When the moon first formed, approximately 4.5 billion years ago, an Earth day lasted around 6 hours. Today it is 24. The moon has been draining our rotation this entire time. In the far future, if the process continued long enough, Earth and moon would reach tidal lock, the same face of Earth always pointing at the moon, the same face of the moon always pointing at Earth. One side of Earth in permanent day, one side in permanent night. The temperature differential between the two hemispheres would generate winds unlike anything in our current atmosphere, but we likely won't get there. Something else happens first. In approximately 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant. It will engulf Mercury, then Venus, possibly Earth itself. But well before that, in roughly 1 to 2 billion years, the sun's increasing luminosity will heat Earth's surface enough to begin evaporating the oceans. Without liquid water, tidal friction changes. The mechanism driving the moon's recession weakens. The retreat slows. This is not reassuring, because by this point something else has already changed. The moon further away appears smaller in the sky. Total solar eclipses, a phenomenon unique to this moment in Earth's history, where the moon and sun appear almost exactly the same size from the surface, will have ended. A coincidence of cosmic geometry that will never repeat, already gone. And the gravitational influence weakens proportionally with distance. The axial stabilization the moon provides becomes less reliable. The wobble begins. Let's talk about what a destabilized axial tilt actually means on the ground. At high obliquity, Earth tilted severely, the polar ice caps would be exposed to direct sunlight for months at a time. They would melt, sea levels would rise by dozens of meters. Coastlines that have existed for tens of thousands of years would vanish. Ecosystems built around predictable seasons would face conditions they have never encountered. Not warming, not cooling, chaos. Unpredictable, oscillating, relentless climate chaos over thousands of years with no stable endpoint. Life does not go extinct immediately, but it reorganizes violently. The species that survive are not necessarily the complex ones. Complexity requires stability. Bacteria do not. The last time Earth experienced even moderate axial instability, it was not gradual. The snowball Earth events, periods where ice sheets extended to the equator, were in part driven by orbital and axial dynamics. Life survived, barely, as single-celled organisms clinging to hydrothermal vents. That is the low end of the disruption spectrum. There is one more thing worth considering. The moon does not just stabilize our axis, it regulates our tides. And tidal cycles may have been essential to the emergence of life itself. The intertidal zone, the region of coastline alternately submerged and exposed by tides, is one of the most biologically active environments on Earth. Many researchers believe this zone played a critical role in the transition from marine to terrestrial life. The rhythmic exposure to air, sunlight, and water created conditions for early organisms to develop tolerance for both environments. Weaker tides mean a smaller intertidal zone, less variation, less pressure to adapt. The moon didn't just protect life on Earth, it may have helped create it, 3.8 centimeters per year. In a human lifetime, the moon moves less than 3 meters further away. You will never notice. Your children will never notice. No living person will ever experience the consequences described here, but the universe does not operate on human timescales. It operates on geological ones. And on geological timescales, 3.8 centimeters per year is not nothing. It is the slow unwinding of a system that has held this planet stable for billions of years. The moon is not abandoning Earth out of indifference. There is no intention here, no drama, no warning, just physics, doing what physics does. Quietly, constantly, without exception. Every night you look up and it is still there, slightly further than yesterday.